you have a little negative charge there, and then you protonate, so you get this. And there you go. You did an addition. You can do the same thing in acid, except that you need to... I hate that they're lazy with this. You need to show me your protonation step, like with a little hydrogen, and just like, all I had to do was draw a little arrow right there. And then they would have actually been showing it, but no. But in acidic conditions, we're gonna have to protonate that first so we don't make a negative charge on our oxygen, because, well, that would be a deprotonated alcohol, right? When we pick this up, O minus, that's basically deprotonated alcohol, right? So if we do pKa, like looking at pKa's, we can kind of tell what things are allowed to have like negative and positive charges in acidic and basic solution, right? Does that kind of make sense? So pKa of an alcohol is like 15. So if we're an acid, we're definitely not forming deprotonated alcohols, right? We have to get pretty basic for that. So then we attack, same as before, and then we may or may not need to get rid of a hydrogen there or something. And yay, we can do nucleophilic addition in acidic and basic environments, just like chapter 16. But there's something special, because what we called Y before, a lot of those Y groups, now that we've got these carboxylic acid derivatives, a lot of them are pretty good leaving groups, or can be turned into pretty good leaving groups. So we don't just have to do nucleophilic addition, we can do nucleophilic substitution. We can, well, I guess I drew it right here. You can nucleophilic attack, and then reform that oxygen double bond, because we really like reforming oxygen double bonds, and kick off a leaving group. And then we replaced the leaving group that was there with our new nucleophile. Same thing in acid, but we get to protonate first, and then, depending on the nucleophile, possibly have that protonate first. Attack, have a positive charge, get rid of that, then you reform. Yeah, deprotonate that. Oh, and then protonate this guy, the leaving group. Then you reform that, kick off the leaving group, you have a positive charge and get rid of the hydrogen. So this is the essential, this is it. This is just a bunch of hydrogen, a bunch of proton transfers so that our charges stay right? But like, attack with a nucleophile, reform your double bond, leaving group leaves. Kind of like 16, but now we get to reform our carbonyl. So those are a lot of the characteristic reactions of carboxylic acid cousins. Relative reactivity. Carboxylic acid derivatives, the ones discussed in this chapter, which is why I'm like, all those things with the sulfonic acids and phosphoric and everything, we're not really, I'm pretty sure this chapter like doesn't even touch chemistry on that. So, yeah. This is really what we end up talking about in this chapter. Amides, esters, anhydrides, and acid halides. This is increasing reactivity toward nucleophilic acyl substitution. So, increasing reactivity toward nucleophilic substitution is going to be a mixture of, on this side, well, I mean, so we've got nucleophile, electrophile. We've got some good electrophiles all over the place here, right? Really, what I'm going to look at for nucleophilic substitution is going to be how good is the leaving group, because how good the electrophile is really only going to influence whether it's attacked, right? But if it's attacked by a nucleophile, then, which I drew in green this time because I hate myself and all of our consistency. Fixed it. If we have a nucleophilic attack, then we get to this tetrahedral intermediate, right? How good of an electrophile that it is, that only affects us getting here. But if we don't actually have a good leaving group attached, then this is just entirely reversible, and this step isn't going to happen, because if what was originally there is not a good leaving group, then whatever attacked it in the first place is probably going to be the thing to leave, if it can, right? So you're either going to do addition, this isn't going to want to leave, or you're going to do a reversible addition, where the thing that you added, if it's not a Grignard reagent, most of the time you can unadd it, and you just get a bunch of that left over, right? So that's the difference in reactivity that we've got here. Increasing, these are in order of increasingly good leaving groups. So acid halides, they don't like being around any sort of moisture or anything. Anhydrides, they don't like moisture. Both of those are very easy to react. And then esters, less easy to react. Amides, significantly less easy to react. So that also means, yeah, increasing, God, I want my clicker back. Somebody borrowed it in group meeting and it got lost. And it was, I don't know, it's the kind of clicker I've been using since my master's. So like, I'm very used to it and I don't like these buttons. They're close together and I don't like it. Sorry, that's why this is happening. Increasing leaving group ability, so increasing basicity, right? If this is a really good leaving group, then its conjugate acid is a really good acid, right? Because it's, well, a really good leaving group is really stable. Less good leaving group means that this conjugate base isn't as stable, which means that this, this base is more basic than this guy, and its acid is worse, right? That makes sense? Better base, worse acid, better leaving group, more stable, better conjugate acid, less stable, better base, worse conjugate acid. Yeah? Did that? Okay. So, combined effect of leaving group ability and susceptibility to nucleophilic attack. So it has something to do with the degree of electrophilicity we've got here, but like even more so is going to be the leaving group. It's going to be, this gives us this like order of reactivity. And you can kind of see, I don't know. See it in the colors. But you can see the electron density in the colors. That's fun. Okay, so I like seeing this better. This is a chart that, I copied it, right? We're going to get to this chart after several slides. Because right now, all the arrows don't, like, we haven't gone over any of the arrows. But I really like this, like, flow chart better than just order of reactivity, because this gives us kind of a meaning for the order of reactivity. Top, more reactive, bottom, less reactive, and these arrows are going to be ways that we can turn each of these into whatever else. So basically, the only ways to go uphill are going to be protonate a carboxylate, protonated, deprotonated carboxylic acid, and then from there you can go uphill with SOCl2. Only ways to go uphill. Everything else is downhill. So that means this can be turned into any of those, whereas this can be turned into any of them except for an acid chloride. This is a anhydride, you can turn a carboxylic acid or an ester into any of these, but you can't turn them into, well, you can't turn an ester at least into an acid anhydride or an acid chloride. And then these amides, you can turn them into a deprotonated carboxylic acid. And that's it. So if you want to turn them into something else, you got to go here first, then go uphill, maybe uphill twice, and then you can turn it into something else, right? We're going to get to this in a second after we actually have reactions that we've talked about to put in this framework, but I like this flow chart of, it visually shows increasing reactivity rather than just a little list. I don't know. I like this better. So, characteristic reactions. Catalysis. Reactivity of acid halides. Let's see. Let me make sure. Yeah. So, acid halides and acid anhydrides, very reactive. Common nucleophiles used to interconvert carboxylic acid derivatives will react directly with them without catalysis. So, if you, common nucleophiles used to interconvert carboxylic acid derivatives. I mean, the things that you use to change one carboxylic acid cousin to another one, right? So, deprotonated alcohol, deprotonated amine, those guys are nucleophiles and they can turn some of these into some of the other ones, right? So, common nucleophiles that can do that, an oxygen nucleophile or a nitrogen nucleophile, they will react with acid halides or acid anhydrides with no catalyst. Some form of acid or base catalyst is required for esters and amides. So if you're going to try and react an ester or an amide with one of our nucleophiles, you're going to need acid or base catalyst because those guys are a lot more stable. Acid catalyst, remember, acid catalyst, since our first step in acid catalysis is to protonate that guy. That's the first step. What this does, remember, is make this electrophile even more electrophilic, right? So they're not as reactive, esters and amides. This makes it more reactive. Or base catalysis, when we had this, just alcohol, this is not necessarily going to be a good enough nucleophile to attack a carbonyl. So we put it in a basic enough environment to make it a negative charge, and now it's a better nucleophile. So acid or base, they can make your electrophile better or your nucleophile better. And also they facilitate leaving group departure. So the base is going to be, an anionic nucleophile, better nucleophile. Acid is better electrophile, and both of them facilitate leaving group departure. Or at least, both of them facilitate leaving group departure in different ways. Acid makes it a better leaving group, right? So like OH is not a leaving group, but H2O is a leaving group. So acid, you protonate it, makes it a good enough leaving group to leave. Basic conditions is just, you know what, you may not be a leaving group, but let's just make everything around you so basic that you're not quite as bad a leaving group as you used to be. Because, you know, once you leave, you will be among your kind, right? Like if you put a bunch of, put a bunch of deprotonated alcohols in like a solution, then that being I mean, it was a leaving group before, but like, it's a whole lot easier to kick off what ends up with deprotonated alcohol, right? When, I mean, it's in equilibrium with other deprotonated alcohols, so it's easier to kick it off. Hydrolysis of acid chlorides. Low molecular weight acid chlorides react rapidly with water to form carboxylic acids and HCl. No catalyst needed, you just water and they get angry and they're like, all right, reaction has happened, no longer am I an acid chloride, sucks to suck if you wanted to use me for some sort of reaction, because I already did a reaction, it was this one. Was it useful to you? I mean, I assume not, if you bought the acid chloride from Sigma, because you could have just bought the carboxylic acid way cheaper, so probably was not what you wanted. High molecular weight acid chlorides are going to react less rapidly with water, so if you've got a whole lot of carbons on there, you might have a little bit of time before the humidity just kills it, and you can do some more chemistry with that. If you've got not a whole lot of carbons on there, like, I don't know, work in a glove box or Schlinkline or something, you're going to be oven drying all of your glassware, because even when it's like dry, like most of the time I rinse my glassware in acetone and then just sort of let that evaporate, and that's pretty well dry. Like, I don't do really water sensitive chemistry, but this, just doing that is going to leave, it's not going to be dry enough, right? So in the world of this, you don't need acid or base catalyst. You're going to go ahead and do all of your oven drying glassware and keep everything very dry. All right, hydrolysis of acid chloride. Mechanism time. Yay, mechanisms. Okay, so let's start with, does this stuff make sense so far? Are we good? Okay, cool. Let's start with this guy. That's better. Do you want to use different? We've already got so many different colors. I kind of don't want to do a different color for the leaving group, to be completely honest. Okay. Oh, wait. What time is this class over? What?
40.
9:40, okay. I forgot to set an alarm for when this class ends, so I'll just do that now. And yeah, repeat every weekday. Save. I remembered to turn off my alarm when you guys took your exam yesterday. Did great. All right, so we're gonna do nucleophilic attack, right? And oh, I almost did an arrow from here, but does this carbon have any electrons to push? I mean, not of its own, right? So we start the arrow at the electrons, and let's see, and remember that our arrows, the direction that they are going from where our electrons are and pointing to where our electrons go. So they are a nice little arrow that shows like, here is the path of the electrons moving, which sometimes, a lot of times, feels like what should happen, right? It feels like you should take this thing, which has all the electrons, and attack the electrophile and kick those electrons up there. But when we do proton transfers, remember, don't do an arrow showing me where the proton goes. Show me an arrow where the electrons are going to pick up the proton. So we don't ever care where the proton's moving, we care what's stealing it, right? Does that kind of make sense? Arrows for electrons, not for protons. They can go to protons, but arrows for electrons, yes.
How can water be a nucleophile and like a leaving group? Because in the acetyl formations, we used water, like you would add a hydrogen to an OH to get it to leave. So how can it attack and leave? Like, why wouldn't it just?
So whenever we've had it as a leaving group, that's always been a reversible reaction, right?
Yeah.
So this is just sort of the reverse of that.
Okay.
Yeah, weird, but like, okay, yeah, I guess if that was reversible, then the reverse can happen. Also, we haven't talked about this really attacking yet because, well, I mean, we did the carboxylic acid, we did carboxylic acids first, right? But if we had this attack with carboxylic acid, even if that replaced the OH, it would have replaced it with an OH, right? So if we have carboxylic acids in water and we radioactively label one of the oxygens, one, if we have that in basic solution, if we have that in basic solution, then it does not matter which one we see. And again, okay, I'm gonna draw. So is this how I do that resonance? It kind of looks like this is how I do this resonance, right? Because in the end, that's where that ends up. But whenever you're doing resonance, it's probably a good idea to put in your, show your lone pairs and maybe even show your bonds to hydrogen that are invisible. That way you can keep track of how many bonds does this have and am I taking away? Because if we did that, that just got really, there. If we do that, we're breaking the octet, right? We're taking electrons away from oxygen so that now it's only got 6 valence electrons and one of them shared, so it's got like 5 valence electrons for formal charge things. That's very unhappy, right? So, and this already has an octet, so now we're trying to break the octet in the opposite way over here. So, even though it looks like that, if you put in your lone pairs, you can remind yourself, oh, we've already got an octet on both of these. So really, the oxygens are just sort of sharing and unsharing electrons, right? This way, instead of, oh, this bond to this bond. So we're not moving electrons from bond to bond when we do when we do this kind of resonance, right? We are gonna take them from the oxygen when we can. So if we had one of these labeled in basic solution, now both of them are labeled, or honestly, if it's in acidic solution, then you can have so either way, you can't really tell the oxygens apart. And then if you have